Good morning, friends. It gives me immense pleasure to be here again for my course Engineering Thermodynamics. The course code of this is AAEC02. I am Dr. Dwivedi, Professor, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. My today's topic is basic concept of thermodynamics, and in this I am going to take these topics: introduction to thermodynamics, branches of thermodynamics, equilibrium, systems and types, approaches of thermodynamic analysis. So normally, if we talk about the thermodynamics, this gives the hotness and the coolness. If there is a hot, there is a cool, there will be a transfer of energy. This heat, if you see the next one here, heat, work and energy. Our whole topics of thermodynamics will be on these three issues, that is the heat. Heat can be converted to the work, and this work is also energy, or energy can be transferred to the work. So here just I give some small logo here. Next topic is thermodynamics and the systems. This we have to understand very well before we proceed to ahead. So what is the thermodynamics? Thermodynamics is the science of energy conversion involving heat and other form of energy, most notably mechanical work. It studies and interrelate the microscopic variable, that is temperature, volume and the pressure. So what is the thermodynamics? It is a science of energy conversion which involves mostly heat and other form of energy to convert to the mechanical work. It mostly here we are going to discuss about microscopy, means bigger issues, not the small issues. That the microscopy I will be discussing in due course of time. In the macroscopic case, the temperature, pressure and the volume, these parameters are studied very well. What is the thermodynamic system? A thermodynamic system, a physical system, is a precisely defined microscopic region of the universe that it studies. So if you see here that, if you see, this is here a system, and here is the surrounding. This is the boundary, and total, this is the universe. So this is the meaning of the system here. So a thermodynamic system is a physical system, is precisely defined microscopic region of the universe that is studied. So here if you see in this system, we have the P, we have the V, we have the T. This is the one point. Here we have the P, we have the V, we have the T. So these are the PVT. They are the microscopic topics, and this we will be discussing in due course of time. Branches of thermodynamics. So now we have understood the thermodynamics and what is the thermodynamics and what are the branches of the thermodynamics. The first branch is the classical thermodynamics, which we are going to take in this course. We are mostly focusing on the classical thermodynamics only. So this classical thermodynamics is the description of the state of the thermodynamical system at near equilibrium using microscopic empirical properties, directly measurable in the laboratory. It is used to model exchanges of energy, work and heat based on the laws of thermodynamics. So in this, we are going to describe the state, and each and every state in a system will be defined by the macroscopic properties like pressure, volume and the temperature, and these are able to measure in the laboratory. And in this, the energy will be converted to the work and heat, and based on the laws of the thermodynamics. So this we are going to study about the classical thermodynamics, and our main focus in this course will be classical thermodynamics. Another thermodynamics branch is statistical mechanics or statistical thermodynamics. Gives thermodynamics a molecular interpretation. This field relates the microscopic properties of individual atoms and molecules to the macroscopic or bulk property of material that can be observed in everyday life, thereby explaining thermodynamics as a natural result of statistical and mechanics, classical and the quantum at the microscopic level. So in this, what happened? Every molecules and atoms, how much energy it is possessing and how much it is transferring in a very, very microscopic way. We are understanding, we are discussing. However, in this course, I am not going to discuss about statistical, only classical thermodynamics. But we should understand that what is the meaning of statistical means it is a microscopy. Classical means it is a microscopy. In macroscopy, the pressure, the properties, pressure, volume and temperature, this all can be measured and average value are taken. But here in statistical, every molecules and the atoms, their way of motion, how much energy they are consuming, how much they are transferring, these all things has to be understood. Next is the chemical thermodynamics. Is the study of the interrelation of energy with chemical reaction. Just I have shown that how the hydraulic cells are generated. So H2 plus O2, H2O is equal to H2 plus O2, C plus H2O, CO plus H2, like this, how much energy or how much it can be transferred. This is studied in the chemical thermodynamics. And next is the biological thermodynamics, is the study of energy transformation in the biological system. So this is also a biological means from human body, for the trees, from the plants, from animals, how this energy is taking place. This studies, or your lungs, your brain, this all parts also, how much they are grasping and how much they are transmitting. These things can be studied in this biological thermodynamics. Next topic I am going to discuss about thermodynamics and its equilibrium. I have shown in my previous this thing that for any system there are three, that is energy, this is the entropy, and this is the equilibrium. So before we go for further discussion about this topic, we should understand what is the thermodynamic equilibrium and how these things should work and how this thing can be analyzed. So here we can see that the word equilibrium implies a state of balance. If there are 2 points, their temperature, pressure and other parameters, and another point, these parameters, how they vary and how after how much time they are getting balanced. In an equilibrium state, there are no unbalanced potential or driving force within the system. So if we take the system, if this is the system, this is the system. Equilibrium means 1, 2, 3, 4, 5, so many points are here, n points, but everywhere the state will be same. The state of here 1, state of here 2, state of n, everywhere the same parameters are existing. There will not be any potential difference. There will not be any gradient inside this system. This is called the system. So in this system, everything is balanced. Then we say that the system is in equilibrium. So that is the meaning of equilibrium. Equilibrium thermodynamics is the systematic study of transformation of matter and energy in system as they approach equilibrium. So once we try to study about equilibrium of thermodynamics, in this the system study of transformation of matter and energy in system as they approach equilibrium. So as and when they are in equilibrium and we are doing some laws, we are implementing some laws and equations, those things are called the equilibrium thermodynamics. Most of systems found in the nature are not in thermodynamic equilibrium because they are not in stationary states and are continuously and discontinuously subjected to flux of matter and energy to and from other system. Non-equilibrium thermodynamics deal with such system. So this case, the first case, equilibrium thermodynamics, is an ideal case and it makes our study very simple. So in our study, we will be doing the equilibrium thermodynamics. But in the real nature, it is very dynamic nature. And here we will not find that all the parameters are in equilibrium. But there will be some flux between the matter and the energy. They may transfer and there will be some gradient of heat, gradient of forces, gradient of energy from higher to low or low to high. And this is the real phenomena which is called the non-equilibrium thermodynamics, deal with such a system. Now I will discuss about thermodynamic systems and the parameters. So this we will see here that what is the meaning of thermodynamic system. A thermodynamic system, a physical system, is a precisely defined microscopic region of the universe that is studied. So thermodynamic system is a microscopic. It is not a micro, it is a macroscopic, a big zone. This is the system here. In this, all the points are in the equilibrium. Physical system is a precisely defined macroscopic region of the universe that is studied. So this is the universe here. This system and this surrounding, if you make together, it is the universe. A thermodynamic system is characterized and defined by a set of thermodynamic parameters. So here in the system, if you see, you will have the thermodynamic parameters like state 1, state 2, P, V, T and so much, H, 5, S, all things will be, some parameters will be there for each and every system. So every system will be defined by the some thermodynamic properties. These properties are the parameters like pressure, temperature, velocity, volume, then entropy, and then we have the internal energy, then we have enthalpy. These are all the parameters which should have in the system. And intensive property, and this we can divide these properties into the two groups. One is the intensive, another is the extensive. So an intensive property, that is the parameter, is a physical property of a system that does not depend on the system size or the amount of material in the system. So what is the intensive? It is not depend upon the how much quantity, how much amount, how much size is there. If you see here, just I am putting here, this is the, so if you see here some 1 meter cube, here we have the 1 meter cube, here the temperature is something 25 degree, here also 25 degree, pressure is 1 bar. If you remove this separator, then both will be mixed. So how much will be the, your volume will be 2 meter cube, but temperature will be 25, pressure will be 1 bar. Means this pressure and temperature, they are the intensive property, but this volume, the mass, is not the intensive property, because this has changed, because this is depend upon the size. Size is increased, your volume is also increased. Here it is 2, but here it is 1. So volume is not your intensive property, but pressure and the temperature, it will remain same. This is called the intensive property or intensive parameter. Next is the extensive properties. Here if you see the volume is changed, I will take this same thing. If you take here that mass, here 1, this is the 2, here you have the 1 kg, here you have the 1 kg. If you remove this separator, there will be a volume of this mass of 2 kg. So this mass is not the intensive property. Volume is also not. If it is 1 meter cube, here 1 meter cube, if you remove this, here will be 2 meter cube. So this volume is also not the, volume is the extensive property. Mass is the extensive property. Pressure and temperature, they are the intensive property. But if you take the specific value per unit mass, then it becomes the intensive property. Next, further I am going to elaborate about the thermodynamic systems. So if you see here, all space in the universe outside the thermodynamic system is known as the surrounding. The environment or the reservoir, a system is separated from its surrounding by a boundary, which may be notional or the real, but which by convention delimits a finite volume. So what is the, it is continued from the previous. So this is the system we have discussed. This is the systems, and outside of the system, this is called the surrounding. So all space in the universe outside of the system. So this total is here, it is a universe. So universe contains systems and the surrounding both. So if you want to define the surrounding, so all space in the universe outside of the system, outside of the thermodynamic system, is known as the surrounding. So this is the surrounding. The environment or the reservoir. So this can be environment, or we can say the reservoir is also the surrounding. A system is separated from its surrounding by a boundary. This is the boundary. This boundary may be real or it may be the imaginary. It is not that it is a fixed, or it may be the moving. It may be the flexible, it may be the rigid, which may be notion or the real, but which by convention delimits the finite value. But this boundary will give a limitation of the system, that the system is in this area only, and beyond that is a surrounding. So our focus will be mostly on the system. You will learn in this course very clearly in due course of time how these things are working, the systems and surrounding. We should be very careful where we have to choose as a system and where we have to choose as a surrounding. So these things we have to understand. Systems are distinguished depending on the kinds of interaction they undergo and the types of energy they exchange with surrounding environment. So system we have to very carefully distinguish when we take any laws, and where we have to implement these laws. We should very much distinguish the kind of interaction they undergo and the types of energy they exchange between the surrounding and the environment. So which type of energy, heat energy, work energy, or anything the system is making to the surrounding, or from the surrounding it is going to the system, that we are going to discuss in due course of time in the few after few classes. So this you can see here that I have just one body is here. Okay, here we have a human body is here. So if you see the your all parts of the body, this is your system here, and this is the imaginary boundary. Okay, but actually your real boundary is your body part, your skin, but some heat is generated and this heat may be going up to here. So this is your imaginary boundary. If you take a cup of tea and here it is a hot cup of tea you are taken, some heat will move from here to here, here to here, here to here. But after some time, if you see that the heat is very negligible. You cannot measure. This is your boundary. This is your system inside. This is the system, and this is your surrounding. So like this we have to imagine, and we have to see that how the things are working. So now if you see here, we can divide this thing into different systems. Isolated system. So what is the isolated system? Isolated systems are completely isolated from their environment. They do not exchange heat, work or matter with their environment. An example of an isolated system is a completely insulated rigid container, such as completely insulated gas cylinder. So if you see here, this is the system here. This is here the system, and this is here surrounding. And if you see the system and the surrounding, no exchange of matter on the energy. There is no exchange. It is closed. If you see the flask, this is the flask. Inside we have here we have the tea. If you put the tea here and you close this lid here, this is the flask, here is the tea, a hot tea. So the hot tea, it is, here is the system here, this is here surrounding, and after that it is sealed, isolated. No energy, no mass transfer take place. This is called the isolated system. Now I will discuss about the closed system. So what is the closed system? Closed systems are able to exchange energy, heat and work, but not matter with their environment. A greenhouse is an example of a closed system, exchanging heat but not work with its environment. whether a system exchanges heat, work or both is usually thought of as a property of its boundary. So this you can see as a closed system. In this closed system, energy is transferred from system to the surrounding or surrounding to the system. But matter means mass. Mass will be same. No exchange of mass. No exchange of mass in closed system. Mostly we will be discussing about the closed system in our next topics. So in closed system, energy can go, work can be transferred, heat can be transferred, but the matter, the mass which is containing in the universe or the system, inside the system, will remain same. That will not change. Next, I am going to discuss about open system. In open system, what happened? Energy exchange and or matter exchange may occur. In this, energy will also exchange from system to the surrounding. Matter will also change from system to the surrounding or surrounding to the system. Both are applicable. Open system may exchange and form of energy as well as matter with their environment. So in this, matter and the energy or the work, they can be interchanged from surrounding to the system or system to the surrounding. A boundary allowing matter exchange is called the permeable. In this boundary is permeable. It can allow the fluid to go out, heat to go out, work can go inside or outside. These all things are permissible. So this boundary is called permeable boundary. The ocean would be an example of an open system, like ocean, anything it is coming, nothing will happen to the ocean. Okay, so ocean will remain same. Energy will go, water will come from the river, it will go as a rain, water will be evaporating, but your system will remain constant. So it is a example of a open system, and the closed systems we will be discussing in our all this work. In this course, we will mostly focusing on the closed system of the thermodynamics. Now I will discuss about internal energy. So what is the internal energy? Internal energy is defined as the energy associated with the random disorder motion of the molecule. If you see here that so many molecules are here, all these molecules will be moving here and there and there, and this will be generating some pressure on the boundaries. They will be transferring some energy, some work. So the mass which is containing, every particle of the mass is containing some energy. That is called the internal energy. So internal energy is defined as the energy associated with the random disorder motion of the molecules. So all these molecules will move here and there. They are not in the same energy. They are due to motion, there the gap between the two molecules, their energy level will change. It is separated in scale from microscopic order energy associated with moving objects. It refers to the invisible microscopic energy on the atomic and the molecular scale. So this internal energy, we can say that it is invisible microscopic energy which this system is containing. That is called the internal energy. The internal energy is the total energy contained in a thermodynamic system. It is the energy necessary to create the system, but exclude the energy associated with a move as a whole or due to external force field. Internal energy has two major components, that is, kinetic energy and the potential energy. So in this, if you see that The internal energy, the total energy in the system. It is the energy necessary to create the system, but exclude the energy associated with the move as a whole. So, but it will not move, means from here to here. Only inside the system, how much energy is there, that system is, this is called internal energy. And this move is can happen due to the external forces. This is not allowed. In internal energy, these forces are not allowed. Internal energy has two major components. That is, first one is the kinetic energy, and second one is the potential energy. Kinetic energy due to the motion, and the potential energy due to its altitude. These things are part of the internal energy. For an ideal monoatomic gas, this is just the translational kinetic energy of the linear motion of the hard sphere type atoms. However, for polyatomic gases, there is a rotational and the vibrational kinetic energy as well. So, if you take the monoatomic gases or the ideal gases, mostly we will be studying about the ideal gases. These ideal gases are the monoatomic gases. In this, we can assume that they are moving in the one direction. And the translational kinetic energy of the linear motion of like one sphere. If this sphere is moving, how much energy it is carrying, that energy is called the internal energy. So only kinetic energy, if it is in the unidirectional and the same altitude, only kinetic energy we can assume. But if it is the polyatomic, then there can be some vibration, some rotation, these things will be there. So those type of kinetic energy also we have to consider. So now there are different approaches for the thermodynamic analysis, and we can study this thing, that what are the approaches for the thermodynamic analysis. So there are two approaches for thermodynamic analysis. One is the microscopic, another is the macroscopic. So if we talk about the microscopic, it is the atoms and the molecules, they are moving in the random direction, and their energy, their motion will, and the collision of these atoms and molecules will generate some energy, some power, some losses. These things are part of the microscopic. And when we take as an average of inside the system, we take average this thing, then it is become the microscopic concept. A microscopic properties refers to properties of atoms, while microscopic properties refers to properties of molecules. At each scale size, the properties are further classified in terms of single atoms per molecules or multiple atoms per molecules of different types. When we talk about the microscopic or the classical view, in macroscopic approach, we fix our attention to certain quantity of matter without considering the activities or event happening at molecular level. In this approach, we determine the properties, that is pressure, volume and the temperature, which get affected by the system interaction with the surrounding. So in this macroscopic, we will study a broad area. In that broad area, what is the parameters, especially the pressure, volume and the temperature, P, V and the T. These are the, we are taking as average in this system. That is called the classical approach or the microscopic approach. And when we discuss about atoms and the molecules, then it becomes the microscopic approach. Next, we are going to discuss about difference between microscopic and the macroscopic properties. So this I am going to discuss here. So here if you see microscopic approach and the microscopic approach, serial number 1 is, this approach is certain quantity of matter without the event happening at molecular level. Events happening at molecular level is taken into account. So just I will make one system here, and there are number of molecules. Okay, so if I am discussing about each, I am just 1 2 3 4 5 n. So if I am calculating for each molecule 1 how much, 2 how much, 3 how much, 4 up to n how much, and how much kinetic energy this have, and then I am calculating, you know that in a per there are millions of atoms are there, and for each atom how much velocity, how much kinetic energy, this thing calculation is very difficult task. That is why normally we give approach for our thermodynamic, classical thermodynamics, we take as a microscopic approach. In this microscopic approach, this approach is certain quantity of matter without the event happening at molecular level. We are not considering what each and every molecules are doing. We are not concerned. In total, in this system, inside this, what is the net pressure, what is the net temperature, and what is the net specific value? That is our concern. But if you talk about the microscopic, each molecular, what is the speed, what is the kinetic energy, what is the pressure, everything we have to understand. Second point is microscopic approach deals with the properties which can be sensed by the humans. So these properties can be sensed by the human, or we can measure these properties, or which can be obtained from mathematical relations, or we can obtain from the mathematical relations. A statistical approach is required for microscopic approach since number of molecules are very, very large. So we have to use the statistical approach, and then we can calculate the microscopic properties. It is an average value of the activities happening at the molecular level. So in this, whatever is happening, if you take the average of whole, then it is a microscopic. And if we take individual, then there are real values and hence difficult to measure. So in this case, each molecules n minus 1, calculating pressure, temperature, kinetic energy, potential energy, enthalpy, entropy is very, very difficult task. It takes a lot of, but it gives very accurate result. In order to describe systems from the microscopic, we need very less number of properties like pressure, volume, and the temperature. But in order to describe a system from microscopic approach, we need a very large number of variables. So in this, we need a huge number of variables are required, and there are huge number of particles. So calculation, it becomes very hard and very difficult to undertake such type of calculations. So that we have to take care of. Now I will discuss about pure substances, and this I will take a separate lecture, but I will give a little brief on this. A pure substance is defined as one that is homogeneous and invariable in chemical composition throughout its mass. So what is a pure substance? It is a homogeneous, means everywhere it is the same type of quality is there, and invariable in chemical composition, means their chemical composition is also same, and all the molecules are distributed in a very systematic manner. Homogeneous means that the substance should be in only one phase. It could be either only solid or only liquid or only gas. So if it is solid, means different particles or different atoms should have in the same phases, either solid or the gas or the liquid. Examples are a mixture of water and milk is a homogeneous mixture, while a mixture of water and the sand is not homogeneous mixture. It is called the heterogeneous mixture because it contains two phases, solid and the liquid. So if you see that our milkman, he is coming, this is the milk, pure milk, and here is the water. So in 1 liter of milk, he is taking 500 ml of water and it is pouring. So now it is 1.5 liters of milk. Okay, so it is just for humor sake. So like this, we have to think that the water and the milk, you cannot distinguish. All are same and in the liquid form, and both are in the same matter. And if you take the another case, one is here water and here are some sand particle. If you put this sand particle, it will look like this. Water is here and sand particle is visible here. So they are not homogeneous. They are called the heterogeneous. They are the heterogeneous. Okay. So examples of pure substances is atmospheric air. So atmospheric air is pure substance. Steam and water mixtures are the pure substance, and combustion product of fuel are considered as a pure substance. It is very important while studying vapor power cycle and internal combustion engine. So whenever we are studying, we are assuming that the mixture of water and the this vapors are in the same state. They are the pure substances. The fuel and the air burning is also in the pure substances. We should also understand about two property rule. So what is this two property rule? Which means to determine thermodynamic state of any pure substances, we need only two thermodynamic state. So if it is the pure substances, we need only two, either pressure or the temperature, pressure and temperature, or pressure and the volume, or volume in the temperature. Any two thing if you know, third thing you can find out if it is the pure substance, because in the pure substance your laws of thermodynamics or state equations will be used. So here we have the state equation PV is equal to nRT. So if you know P, if you know V, you can find out the T. If you know the T and the P, you can find out the V. So like this, because these things are constant. So these equations are used for the pure substances of our ideal gas condition. So PV is equal to nRT can be used. So if you know the two parameters, third parameters, you can find out by using the state equation. In the next class, I am going to discuss about properties of the pure substances. Then I will discuss about pressure, temperature, specific volume, and these all properties I will be discussing, and hope this will be very useful for your next classes. These are the references I have taken from P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition, and then we have the Senegal and Thermodynamics and Engineering Approach. Then I have taken this PPT or the video lecture from Thermodynamics from Mishra, IIT Kanpur lecture. This I have taken. Any questions you are welcome to ask. My email is ydwedi@gmail.com. This is my email. Always I recommend to like and subscribe this channel and give comment if you have anything. Thank you very much for joining this class. We will meet you soon with new lecture. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.